Okay, welcome back to lecture. We're going to be doing a lot of work today. We're going to do some dot cam work here towards the beginning of class. And then we're going to go through some outlines of notes and diagrams. We're going to do a ton of clicking, so make sure your clicker is ready. And let me just re-emphasize for you the SI schedule, supplemental instruction. Anybody go on Tuesday? Anybody in here go on to? One person. How did it go? How many people were there? Katie.
I went to both of them. I went Monday morning and then Tuesday. So Monday morning there was quite a few people. Tuesday there was like 2, 3 other people.
2 or 3 on Tuesday. Yeah. Okay, good. So your next session in which you go over this stuff we talk about today and the homework over the weekend will be Monday. So have that in mind. Hopefully you can squeeze that in the morning. Each of these sessions are 50 minutes, 50. So hopefully you can get in there. Let me also remind you to register your iClicker in web courses, and I know a bunch of you have done that, and I helped a few of you double check that this morning, so that's good. If you haven't done that, I know some of you are still waiting for your iClicker, but get that done as soon as you can. And I probably won't update the roster until tomorrow. So if you update, if you get your stuff after lunch today, for instance, and then register here in web courses, I should be able to pick it up after lunch today. All right. This is the last day of practice questions, and it's all scientific questions today. It's not any goofy Chuck Norris questions. And it's also the last day to get a bonus point. Now, Tuesday, we'll be starting to accumulate official participation. So that every click that you start with on Tuesday will go into your 25 out of 25 on your semester grade. Today goes into a bonus point, so it's a little bit different bundle of points. But anyways, another few grading updates I want to review with you. You may have noticed. First of all, there's the early iClicker registration from Tuesday. I put that up for you if you have it. We got another one today, and that's pending, of course. Homeworks and stuff. Now, one thing I did was I went down here. Some of you actually had 2 grades. Not many of you, but a few of you had a grade for the homework 1 that I closed, 01A, that had the blooper in it, and you still got a score and you maxed out or whatever, whatever. And then I asked everybody to do the new version, and so what I basically did was convert the new version into an 8-point grade, and then I took whichever one was higher. So if you maxed out on homework 01A that got closed, then you got an 8. If you got a 7 out of 7 on the new version, then you got an 8 down here in the equivalent score. Okay, so that's the one that we're going to go by. That's the one that we're going to put in the homework. Tally, this baby down here. And for this example student here, the student had a 6 out of 7 on the new version. And so I converted that to an 8-point basis, and so that goes down. Basically, everything from homework 1 gets bumped up 1 point, if that's your maximum. So this guy got bumped up to a 7 out of 8. So that's good. All right. Any questions about that homework? Okay, let's keep going. We're going to do some some more look-see at Logan's run from Tuesday. And we're going to actually use some of the data. We're going to go to the document cam. But before we do that, I have some clicker questions for you. So go ahead and fire up your clicker, and let me start a new session here. All right. And I think we're all multiple choice today, so. Okay. Now, when we did the document cam work on Tuesday, we used the formula delta x over delta t to figure out the average speed. Now, that's perfectly righteous. That's a normal way to get an average speed. There's a more generic formula for average that you can use for the average of anything, however. And let's see if you can spot it from this list. All right. A, B, C, or D. Which one's the generic average formula? You got V's all over the place, but which one is righteous for So think about each of those formulas and maybe jot down the one that you think is right. And let's see what you guys are voting for here. Okay. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, pretty good. Yeah, the correct answer is B. Basically, just add them up and then divide by how many you have, in this case, 2. All right? And that's how you do an average of, 12 people's age, the average of anything. The average mass of 25 donuts or whatever you have. All right? So go ahead and make a note of that. Now, let me ask you one more question. Now, this is related to the skateboarder now. So we've got this V1 bar equals V1 plus V2 quantity in the numerator divided by 2. That's going to be the formula we're going to employ here. But let me ask you this. If the skateboarder is at rest at point P1, as Logan was, where are you at, Logan? Okay. And I was holding Logan back. So what do you write down for his... 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, very good. Most of you got that one right. This is the correct answer. Yeah, V1 is equal to 0. So if you know something's at rest, that's the easy one. You don't even have to think about it. It's just ding, 0. Okay, and that's going to be helpful for us in this formula. Now, here's another multiple choice question. How does the average speed formula in the upper right, how does that simplify if V1 is equal to 0? Choose one of these. Let me start it. Okay. Which one of these, if you think about it, yeah, I see people going like, pointing at the, good. Welcome. We're clicking. Good. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. Most of you guys crushed this. C is the correct one. Yeah, in other words, just take your eraser of your pencil and erase the V1 because it's 0. You don't even have to write it in there. And what's left is V2 over 2. Now, we're going to use that nice result for a dynamical system that starts from rest to simplify and get some data out of our measurements from Logan's run. And what we're shooting for is this idea of accelerations. Now, as I believe I mentioned last time, this is Galileo's basic insight into acceleration. He was looking at free fall, the famous free fall experiment from the Leaning Tower of Pisa, which, I had a friend that showed me a photo, a friend from when I was growing up in one of my elementary school friends went to Italy over the summer, and she went to Pisa and had this excellent, I should dig out that photo. She had this excellent photo of the Tower of Pisa, the Leaning Tower of Pisa, and it is amazing how it looks. You definitely can see that it's tilted. It's very noticeable. And it's still up. I mean, it's amazing that it hasn't fallen over, but I observe a stone initially at rest. Same as Logan. All right? Falling from an elevated position. Now, he wasn't falling. He was kind of sliding down on a ramp, on a slope down here of the aisle. And I don't think Logan would have volunteered to drop 10 meters from the roof down to the ground. But and Galileo used a cannonball and a musket ball. And he said that they initially fall from rest from an elevated position, continually acquiring new increments of speed. So underline that concept, acquiring. The force of gravity is giving, on the way down at least, it's givething extra downward speed. And he said it's acquiring new increments of speed. Now we're going to go into that idea of increments of speed and try to make sense of it. Letitia.
I have a question, but it's about the previous question. I learned physics in Portuguese, so sometimes I get confused.
Uh-huh.
An object being at rest doesn't depend on the reference.
It does. That's right. That's right. You have to. Yes, if we were. Letitia's thinking about the theory of relativity, which means all these things. This is pre-Einstein. The two guys that figured all this out were first Galileo and then Einstein. And what you're talking about is the theory of relativity, which means if you're in, there is no absolute state of rest in the universe. It depends on it depends on the state of motion of the observer and the object that's in motion or at rest. So for one observer, something might appear at rest, but another person that's in motion might think, dude, that it's moving towards me or it's moving away from me. All right? But we're going to keep with Galileo's viewpoint. Yeah. So we're just going to say that you can think of it as the observer is at rest with respect to the cannonball at the beginning of its motion. Okay. Now we're going to go to the talking. We're going to do something called a talking PDF on the document cam, and that's using my smart pen, which I'll show you here as soon as we turn on the document cam. We're going to use the average speed and standing start, v1 equals 0.00 meters per second. And we're going to use Galileo's definition of acceleration. It basically corresponds to this formula. Go ahead and jot this down. A equals delta V over delta T. And then we're going to return and look at velocity graphs. We were talking about the tortoises and the hare's velocity graphs last time. We're going to go back to the tortoise, and then we're going to forget about the hare because he's a loser. And we're going to talk about the skateboarder and make a velocity graph for that. And then we're going to make a generalization for any accelerated system using velocity graphs. All right, and we're going to start with the talking PDF on the document cam. Now I'm going to pause the lecture recording for just a second. Let's go back to this. Okay, we're back in recording. Let's talk about these distance polygons now. Okay, so basic velocity versus time graph. This is the first one we did. 1 meter per second. He's moving to the right. Positive means rightward. If we had somebody moving to the left, if I get, here's how we could have done it. If I shoved Connor uphill for a bit, he'd have a little bit of negative velocity in this system. Horizontal axis represents time. We usually start the graph, but we don't have to. We could start it anywhere we want, Axel. But 0 is good. And so this guy is graphed out for the first 2.5 seconds, and that's just a number I decide to, some nice round number. But in the skateboarder distance triangle graph, velocity graph, that was 6.4 for the elapsed time. But for this one, it's just 2.5 seconds. Okay, so here's a sentence. The object is moving at a constant velocity of 1 meter per second rightward for 2.5 seconds. All right. The graphed line, or the dashed line, is the actual velocity graph. And it's similar to the tortoise's velocity graph in the textbook. Hey, raise your hand if you got these textbooks squared away so far. Raise your hand up. All right, good. The rest of yous, we're going to need it, so you better get going on that. And as I mentioned before, this graph encodes all instants of time visually. All right. So what we measured, we made some physical measurements on the aisle at 2 instants of time. Time t equals 0 times t equals, whatever Katie and Evan came up with. But this thing encodes all of them visually in one graph. Now, we shade in the rectangle. Go ahead and shade in your rectangle. And I didn't do it on the talking PDF because it kind of bloops up the diagram. But you can shade it in, and I'll put a little red side bar on it, just so it looks like a nice rectangle. So there's your rectangle, and that's what we would call a distance rectangle, because the area represents, base times height. That it represents, and here's the cancellation. Call it. Seconds cancel. The base is 2.5 seconds, and the height is 1 meter per second, and the seconds cancel, so you're left with a total. And so, as I mentioned, it's kosher to interpret that shaded area as the distance traveled to the right. Now, if you have some other, if you're moving to the left, you're going to be below the time axis, and you're going to have a different looking rectangle maybe. All right, but you interpret that as distance traveled to the left, all right, or negative distance, negative change of coordinate. All right, and all of this jives with the distance formula. Okay, and Connor, this is what you were asking about. Speed times time. That's how you get a distance. Delta x is equal to speed v times delta t. And in terms of the velocity graph, that's base times height. So area of that rectangle. So it works out. And this is the most basic velocity graph you can have, other than zero velocity, at rest, just on the time axis. You don't capture any new speed. All right? And so that perfectly jives with that. Now that's the tortoise. We're going to talk about an accelerated system. We already made it, a distance triangle. Let's go into it in detail. All right, so here's the velocity formula. And this is related to what we attributed to Galileo, that the amount of velocity change or increments of speed, delta v, continually acquired over some elapsed time, delta t. So that's continually acquiring over some delta t. And hey, you guys, you know what this quantity is in the velocity graph? This is rise over run. Ooh. I just blurted out the answer for a question that's coming up. Well, you guys will probably still get tripped up on it. So an acceleration, if you think about it, this is a side note, and we're going to actually use this. An acceleration, if you know the acceleration, which we now know for Logan's run, 0.44? Okay. We can now figure out, for another 4 seconds, how much speed is he going to gather? So that'd be 4 times 0.44. So that'd be 1.76 meters per second for another 4 seconds. Okay, so we can always figure out additional delta v or any delta v if we know the acceleration and the elapsed time. So that's this formula here. So jot this one down. This is the change in the velocity if you know the acceleration and the elapsed time. All right. Now, we're going to do a distance triangle for an object that is slowing down. All right, so this is a little bit different from Connor's triangle. Now, we got Connor's triangle. That's good. We kind of already know what to do with it. It's a distance polygon. Let's do this one. This is an object that's slowing down. It starts at 3 meters per second, rightward. And after 4 seconds, it has come to a stop. All right? So you could write that down as a sentence. This object, it had initial speed 3, and it stopped. It came to a stop in 4 seconds. Okay? So this is somebody, now 3 meters per second, that's about 6. This is somebody jogging, and they're out on the track, and you're out by the track, and you time them from jogging past you at 3 meters per second, and then 4 seconds later, they've slowed down to a stop, and they're drinking some Gatorade. Connor?
Can we assume the velocity is always going to be meters per second?
Yeah. Well, it's whatever. You can't assume that, but do assume it here, because I kind of have it in the notes that it's 3 meters per second. Somebody's calling me. But I'm not. We're never going to do feet per second or miles. We're going to talk about miles per hour since everybody uses that in their car, but usually all our main things are going to be meters per second. Okay, shade in the triangle. All right, and I shaded mine in blue. All right, so there's our distance polygon. It's a distance triangle, and we're going to analyze it. 1/2 base times height. So let's figure out the area, 1/2 base times height. Okay, base is, what's the size of the base? 4 seconds. And how big is the height? 3? Incorrect. You got to have the units in there. 3 meters per second, that's right. Okay, so here we go. So there's the area. It's 1/2 base times height, so the base is 4 seconds. And the height is 3 meters per second. And again, I get cancelization, but I'm not going to cancel yet. You know, you can do that right now, but I want to mess around with 3 meters per second and that factor of 1/2 that's parked out front. All right, so let's put those two together. All right, so 4 seconds is still in its own parenthesis. And then, but I put the 3 meters per second and a denominator of 2. Does that quantity have a name? Think about that. 3 meters per second divided by 2. It's the average speed, that's right. So this is delta t times the average speed. And Connor, here we go again. Delta t times average speed. But now, this is the average speed is the amount of speed that you've lost divided by 2. You've lost, by the time you've stopped, you've lost 3 meters per second. All right. So it's 3 meters per second divided by 2 is the average speed. And the average speed, the amount of speed that you've lost, is also A delta t. All right? So the amount of speed that you've gained is A delta t divided by 2. That's the average speed now. All right? So V2 here, actually, A delta t represents V1 because it starts in motion and the other endpoint is 0. So this is like the opposite of what Connor was doing. He started at 0 and acquired a final top speed. And this is kind of the reverse of that. So the average speed is A delta t divided by 2. Now let's put that in. All right, so here we go. We got a delta t and an average speed. So the average speed is another A delta t and a 2 in the denominator. So D, the average speed, is replaced by A delta t over 2. So the distance is delta t times A delta t divided by 2. And hey, you guys, that corresponds to, in more simple notation, 1/2 AT squared. So instead of writing delta t quantity squared, we're just writing t squared. And do you remember that fancy formula that I talked about on last Thursday? YF equals YI plus VIYT plus 1/2 GT squared. Remember that? That was that formula with that 1/2 AT squared in it, or 1/2 GT squared in it. That's what this is. That formula has a distance triangle. This is the distance triangle generic version. So for something that's coming to a stop, or for something that starts at rest and acquires a final speed, like you drop something off the top of the library, 1/2 AT squared. Or in the case of gravity, 1/2 GT squared. So there's your general formula. Okay? And that's for this distance triangle. Now, on Tuesday, what we'll do is, would you guys like to dismiss a few minutes early today? Okay. I think we might be able to do. We have some clicker questions coming up. But what we'll do is I'll show you actually how NASA uses distance triangles and distance rectangles to figure out what these big rockets are doing, but they use delta T that's very, very small. They have to use delta T equals, like a millisecond. Because every millisecond that those rocket motors are burning, they're blazing out tons of rocket fuel. All right, and it sets up the acceleration and everything, and it's pretty bodacious. But I'll be showing you that on Tuesday probably. Now let's do a few more clicker questions, and I've got a brain burner for you. And the brain burner, it's been nice knowing you. Let's see if I can fry your brain with this question or with this diagram. Now, this one is a deluxe velocity graph. We got distance triangles in here, but the graph cuts down below the time axis. All right, V0 is positive 2, and V of 2 seconds is minus 2 meters per second, and it's a straight line. All right, so you would have two, different velocity triangles to do here, but you could do them. 1/2 AT squared, 1/2 base times height. Yeah, you could do it. All right, so let's do a couple of questions about this. Let me get my... Okay, so here's our next question. The full graph shows the object doing what? So read carefully and think. And as with everything that you do in this class, you want to read carefully and think, especially on exams. Do not let me catch you napping on exams. I have my cell phone must be off or something. Oh, the ringer's all the way down to 0. Okay, that's better. Think. Talk with your neighbor, What do you think? What does your neighbor think? 25 seconds. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, you guys are doing good here. Yeah, the correct answer is this. And let's take but some of you voted for A, some of you voted for B. Nobody voted a majority for C, correct. That was the most, 45%. You win the election, but it's not a majority. 27% voted for D, and nobody voted for E. Okay, moving rightward for the entire 2 seconds, that is no go. So if you vote, you should make a note about this. These should be going into your notes about this diagram. Because this diagram has some stuff above the time axis. That's rightward motion. All right? And it has some of the graph below the time axis. That's leftward motion. So A is out. It's got a second of rightward, and then it stops, and then it's got leftward motion. B, some of you voted for B. Constant velocity? No way, Jose, because it's not flat. The velocity is changing. It starts at 2, and it just keeps decreasing. Question?
Well, I figured that if it's going, it's not a straight line, however, it's straightly diagonal, I guess you want to call it. So wouldn't that be constant, that it's constantly decreasing?
Not the velocity. The velocity is not constant, but Good, you're thinking. Good. Something else is constant, but not the velocity. And we're going to get to that in a second. But let's look at answer D. The slope is negative, which is true. It is dipping to the right. So the object is moving leftward. Yeah, it does have a negative slope, but that doesn't mean it's moving leftward. Only if it's below the time axis do you have leftward motion. All right. So up here, you've got positive velocity. You're moving to the right. Down here, you've got negative velocities. You're moving back to the left. And right here is your stopping point. So at time t equals 1 second, you're stopped for just an instant of time. Now, let's look at this graph. Again, here we go. Here's another question. And Connor, this is building up to your answer. Question number 4 for today. The run of this graph is 2 seconds. The meaning of it is, and hopefully this one's an easy one for you. 30 seconds. $20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. This is good. 86 answers. Very nice. Okay, now 60% of you answered correctly on this problem. Here's the run. Okay. And that's simply the duration of the motion. All right. And that's the amount of time that, Katie or Evan would measure. It's not the distance traveled. You know why? The run is not an area. It's a sideways distance on this graph. And on a velocity graph, it's the area that corresponds to a distance. It's actually the object's acceleration. Incorrect, because the run is 2 seconds is a time interval. It's an amount of time. It's not an acceleration. So an acceleration would be, something meters per second squared. But this is just seconds. Object's delta V, no. The object's delta V is somewhere else. And there is no acceleration. No, that is not true either, because the velocity is definitely changing. It's rightward velocity, then it stops, and then it starts going to the left. So make a note of it for this, for the run. Now, next question. The rise. And here's the rise. Okay, so the rise, and it's actually a dip, so it's a negative rise. It's dipping down to the right. The meaning of this is $20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Come on, you guys. 0. Come on, make a decision. All right. Yeah, it's just the delta V. That's the delta V. All right. So the run is your delta T, and the rise, whether it's a negative or a positive, that's your delta V. So this would be negative 4 meters per second of delta V. All right? What's the rise over the run for this graph? Connor. This is your question. This is what you were asking about. I see a lot of people thinking, but I don't see a lot of people consulting with neighbors. But you may do so. Now, you can't on the test, though. This is good. We got a majority of correct answers, but I'm still tripping up. Rise over the run. What do you call that? Rise over the run? Slope. Yeah, so the slope of a velocity graph has a physical meaning. All right, 10 seconds, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, you guys are geniuses. 80% of you got this right. Yeah, that's the accelerate. Delta V over delta T. Delta V is the rise. Delta T is the run. So rise over run is delta V over delta T. That's the acceleration. All right. So now here's a sentence to describe what's actually happening. And you can add this into your notes. The object slows down, stops, then it starts acquiring leftward speed. So you know what that's like? It's like, it's like you, you're in a parking lot, and somebody gets the car moving, and you and your buddies push back on the car, and for a few feet you're backing up, but you're slowing it down, and then you're gradually slowing it down, and then you stop, and you keep pushing, and then you get the speed going back the other way. So that would be an example of it. All right, so rise over the run, delta V over delta T. And in this case, go ahead and write these numbers in. -4 meter per second on top, and 2 seconds elapsed time in the denominator. So your acceleration is 2 meters per second. Okay? So every second of pushback from you and your buddies, you're changing it by 2 meters per second. And after 2 seconds, it's going back the other way. And here's the other way to write that acceleration. -2 meters per second squared. That's also good. All right? So let's do a recap. Let's do a question first. Connor.
Is it possible to have the object slow down, not stop, and then get leftward motion, or does it have to stop every time?
It's going to have a turning point. You have to go from rightward to leftward. You're going to have a point where it's one instant of time when it's 0. Same thing as a baseball. You hit a perfect straight pop-up. It'll slow down on the way up, come to for just an instant of time, 0, but then starts acquiring downward speed on the way back. So yeah, there's a turn. It's important. It's pretty important physically. It's called a turning point of the motion, and there's going to be one. Call it.
Now, when you say rightward and leftward, it doesn't necessarily mean it doesn't have to be going to the right, going to the left.
Yeah, it does. That's how we're interpreting it here. But if I tell you, I could easily do, and on Thursday what we'll do, we're going to dismiss in a minute here, but on Thursday what we're going to do is talk about pop-ups and baseballs. And then the positive will mean upward, and downward, and negative will mean downward. So it just depends on the context. We're not done. We still have a little bit of notes. It's not quite closing time. We'll do that on Tuesday next week. We got it. We're going to be doing it. All right, so let's do a recap and tell Professor Galileo what we know. Okay, constant velocity. Area under the curve, area under the graph, V delta T. That corresponds to delta X equals V delta T. Or here's a pretty simplified version of it. Connor, distance, speed times time. Yeah. And we know that the velocity graph is a horizontal line segment, and that the distance rectangle corresponds to any equation that has a speed times a time. Whenever you see a speed times a time, then you've got you know that you can model it as a distance rectangle in some way. All right, now accelerating systems from rest or to a stop, Vf equals 0. Yeah, we can do that. And those are going to be 1/2 at squared, 1/2 base times height. So that's the distance triangle formula. The velocity graph is a sloped line segment of some kind. All right? Whatever the slope happens to be. All right? And it corresponds to a distance rectangle, a distance triangle. All right, so that's kind of our summary of concepts, formulas, and distance polygons. Now, what we're going to talk about next week is this. What if the velocity doesn't change uniformly? What if you have something that's not a straight line segment? Like it kind of curves, in some way. We can deal with that. And in that, if you have Netflix or you actually own it, I would, for homework, in addition to the homework that I'm about to announce, get a copy of that movie, Hidden Figures, that came out a couple years ago about Katherine Johnson and all her workmates up in Virginia. Wonderful movie, and actually highly appropriate for what we are doing. So here's your homework. Homework number 2 will be in web courses. Look for it by lunchtime tomorrow. It'll be based on this lecture. So you won't need the book absolutely, but do try to get the book. It will help. And we're eventually going to have homework in the book, but not this weekend. So homework number 2 in web courses, and watch Hidden Figures. You're just